Whether swiping a credit card or checking GPS, you are relying on a massive, invisible web of satellites routing data from space. Looking at this scale diagram, outer space is obviously massive, but the specific region we actually use to run modern civilization, low Earth orbit, is an incredibly narrow, crowded band right against the planet's surface. For decades, reaching that orbital band required massive state budgets. It was an exclusive domain of careful, bespoke engineering and very low launch volumes. Today, the cost of spaceflight has plummeted. Commercial rockets launch constantly, rapidly populating those same narrow orbital bands with thousands of new commercial devices. The danger in this crowded environment doesn't only come from giant spacecraft. A 1-centimeter paint fleck traveling at 17,500 miles per hour strikes metal with the kinetic energy of a hand grenade. A single collision mathematically turns one projectile into 10,000 new ones, setting off a chain reaction. The math governing this environment predicts a chain reaction called the Kessler Syndrome. It states that once the density of objects in orbit crosses a certain threshold, one random collision will inevitably trigger another, and then another. We have already seen this physical reality in action. In 2009, a defunct Russian Cosmos satellite drifted directly into the path of an active U.S. Iridium satellite. The two bodies struck each other at over 26,000 miles per hour, instantly shattering both multi-ton spacecraft. This data map of low Earth orbit displays the immediate fallout. Within seconds, that single impact generated over 2,000 pieces of high-speed shrapnel. Orbital mechanics dictate this localized debris cloud doesn't stay in one place. Over time, it spreads out, forming a fast-moving web that aggressively slices through flight paths of other active satellites. The 2009 collision confirmed that orbital debris is a dynamic, exponentially multiplying threat. Left unchecked, our own destroyed infrastructure becomes the very weapon that shreds everything else in orbit. The absolute limit of this multiplication is a mathematical threshold known as critical density. This cross-section diagram shows our planet's natural defense mechanism. Atmospheric drag constantly grabs low-orbiting debris, slowly pulling it down until it harmlessly burns up in the upper atmosphere. Critical density occurs when the rate of new debris generated by space collisions mathematically surpasses the speed at which the atmosphere can clean it up. The debris becomes permanently trapped. The result is a self-sustaining chain reaction. Collisions happen continuously, eventually forming an impenetrable shell of high-speed shrapnel, completely encasing the globe. Reaching critical density means sacrificing our modern infrastructure. It creates a physical barrier of metal that would trap humanity on the surface of the Earth, rolling back decades of technological progress. Stopping the cascade requires a feat of precision, capturing high-speed, tumbling shrapnel in a vacuum, without fracturing the metal into even more debris. Engineers are developing radical prototypes to answer this. They are testing magnetic space tugs and robotic craft programmed to perfectly match a satellite's chaotic spin to deploy robotic capture nets. Building one prototype is difficult, but scaling it up presents immense logistical and financial barriers. Deploying a cleanup megaproject large enough to scrub thousands of pieces of debris requires funding on a global scale. Space agencies and commercial companies now face a pivot. They must move past unchecked expansion toward active, coordinated stewardship of the orbital environment. Low Earth orbit is a finite, fragile natural resource that requires aggressive management to secure any future for space travel.